Hello, wishing you all a good day. So, we continue with our design of absorber session, and to start with, we have a very short recapitulation of what we talked about in the last class. This is the figure which you had seen, and where we had found out two things. We had found out basically L dash minimum. We had before that we found out G dash, which is basically these two are the solute free flow rates in kg mole per hour or something like that, and we definitely do have the corresponding total molar flow rates as G and L. Rather, this should be L mean, but one thing we understand that this varies along the column, and naturally L mean will also vary along the column. That's the liquid flow rate across the individual ideal stages. And here we have capital N number of ideal stages as shown and as we have talked about earlier. We have found and we have told you how to draw the operating line. The operating line has to be drawn with a particular L operating value, which is basically typically around 1.5 times L minimum. Now, what we have done is we also have told you that how to determine this L minimum, because under this L minimum condition, this particular concentration is basically Xn star, which is in equilibrium with the corresponding Y here. So, obviously, here we have a small x and small y, which are the mole fraction coordinates. We have the equilibrium line here. The equilibrium line goes like this. This is the data we have collected from literature, and this is the starting point and this is the end point here. So, this end point concentration naturally will in this time, when we have L dash mean as the flow rate of the solvent, this is definitely your Xn star, which is in equilibrium with Yn plus 1. That is what we have told right now. We also have derived an equation of the operating line. The operating line starts here and it keeps on going and it grows here like this. Now, in the operating line, how is the operating line based? The operating line equation is based on simply the mass balance around this envelope. What you have here, we have, say, if my L dash operating is the flow rate of my solute free solvent, it starts with a concentration of X0 and goes to a concentration of Xn. So, naturally, this is the increase in change in concentration. So, that is the pickup of my solute, which also has to match the pickup of my solute from the gas phase. The gas phase enters with a composition of Y. Sorry, this we can put a small n, and this will be n plus 1, and whatever goes out is with a composition of this. I will just make the correction here. Here I have the eraser, so I just improve this and make it more correct. And so, this basically is Xn. Now, in a general sense, when we are trying to say this, basically here what we have is a relationship between Yn plus 1 and Xn. We know that in mole fraction basis, the corresponding values are Yn plus 1 and Xn. So, the same relationship could also be written in terms of the small y and the small x, and it could be generalized. In the last session, the slide that we have shown, we have given a generalized equation which relates this y and x, and this y and x are basically the concentration of the components of vapor and the liquid here, their concentrations. Now, what we do is we have a very similar procedure. The top end of the column is having a composition of X0 and Y1. We know these are the parameters known to us already. We know the inlet concentration Yn plus 1, the exit concentration Y1, because that is the task. The amount of solute that has to be removed, and after removal the concentration has to come to Y1. We also know the flow rate G dash. Now, we are going to do this for a flow rate of L operating, which is nothing but about 1.5 times L minimum dash. We know L minimum dash, so naturally L dash operating is also known for us. So, what we do is we start drawing this operating line based on this L dash operating value of 1.5 times L minimum. Now, what we do is we basically have a relationship between x and y. This is basically the operating line equation. This will be more clear when we deal with an example with specific numerical values. Now, if I know an x, if I assume an x, I can always calculate the value of y, and we know what is the minimum value of x. The minimum value of x is basically x0, and what's the maximum value of x? That corresponds to xn star. So, what we do is we vary small x from small x0 to small xn star, which is the equilibrium, which we have just found out as well, and we find out the corresponding values of y, and we plot it here as an operating line. This end is basically on the operating line is what? This end simply tells us that it is the corresponding composition here and here. So, naturally the coordinate of this point will be x0 and y1. Now, what we also know that if we move here, what we have corresponding to y1 the corresponding composition of the liquid phase. So, this basically has got the composition x1, and what we do is this particular thing, if I go up, we will find another operating point in the next stage, and we keep on moving like this. This I did not say in details, but what we want and what we feel here is obvious, that the procedure is exactly the same as the McCabe-Thiele construction that you have done in case of the binary distillation, and the procedure is absolutely the same. Here I would just like to add one more thing, that in this specific case of absorber, this construction looks like this, and all these triangles that we make are above the equilibrium line. In case of stripping, the operating line falls below the equilibrium line, and such triangular constructions are constructed below the equilibrium line, but the procedure is exactly the same. With this in brief, we have found that after 1, 2, 3, after the third stage, what we have is basically we have exceeded yn plus 1. What is the physical significance? That means if I have instead of yn plus 1 a higher value which corresponds to this, which corresponds to the ordinate of this, even then we will be reaching the value of y1 under this operating condition with L dash operating. So, what we can say is this is a safe design with a very small amount of margin also. If we want to be exact, we will only say that well, we really do not require 3 stages, we do not require 4 stages, we require about 3.8. So, with this we will move on, and this is how you find out. Here what we have is nothing but the same thing written in a stepwise set of instructions, and what we have is basically how to plot the operating line, and it has to cover the entire range of interest for x and y. For x, naturally it is x0 to your xn star, and this exactly is the procedure for finding out the number of stages required, which we already have demonstrated. Now, we have another case. The case that we have dealt so far deals with a little bit higher concentration of the solute in both the phases. Now, when we know that when my concentrations are small, that means my x0 is very small, yn plus 1 is also very small. That means both the inlet concentration of solute in the liquid and the vapor phase are small. In that case, capital X and small x and capital Y and y are almost same. So the operating line equation is approximately this. So what we have here is a simplified expression for the operating line equation. We also know, and what we find here, this basically is a relationship between y and x, and it is linear. That's the major thing. And we know that under dilute solutions with low concentration, the Henry's law is valid for most of the systems. So what we write here, y is equal to h into x star, h being naturally the Henry's law constant, and this is also a linear equation. Now when I say this, it is possible for us to derive an analytical expression for the number of stages required. Now this analytical expression involves one thing. See, basically what you have here is an x and a corresponding y, and what you have is a linear equilibrium relationship, and what you have here is a nearly straight, I'll put it here in a nicer way. This is x, this is y, and this is basically your y is equal to hx, which is the equilibrium line, and here what you have is your operating line, which is also, this is your equilibrium line. Now when you have to go from x to x0 to x1, x0 to xn, or the value of y has to go from here to here, the numerical number of it can be numerically, in fact it can be geometrically found out, or rather it is nothing but having an analytical expression for this particular geometry, that how many number of steps are really required in order to go from one particular point, from this point to this point. So what we find here is the expression is this, and this is called the Kremser equation. It is a very famous equation which is based on the linearity of the equilibrium line as well as the operating line. Now there is something else. This involves a constant A, which is known as the absorption factor. What is this absorption factor? It is written here L upon m by g, which is also same as L by g divided by small m. And what is the small m? The small m is the delta y by delta x for the equilibrium line. And what is L by g? This is basically the slope of this. So this absorption factor is the slope, is the ratio of the slope of the operating line to the equilibrium line. Both are linear. So the so all through the range of concentration change, it remains constant. Now if you are trying to handle a situation in which the equilibrium line is slightly carved, so you may have one slope here and another slope here. One slope is m1, the other end the slope is m2. In that case, but they should not be too different. What is typically done is you use the value of m1 into m2, and it has been found that it also gives pretty good estimation of the n. Now remember one thing, the Kremser equation is primarily used for dilute solutions, and quite naturally we will see that the diagram that we have there, our operating line is rather carved, but the equilibrium line is fairly linear. So even if we use Kremser equation, we try to use Kremser equation in that over there, what we will find that it will be giving us an approximate value of the number of stages. We have an case of absorber design example with us. The absorber is using fresh water as solvent for removal of SO2 from air. The total flow rate of the air is 6.5 kilomole per hour, and it has got 20% SO2. So quite naturally 20% of SO2 is 1.3 kilomole per hour SO2, and the rest amount is basically the inert water, is inert air, and it is brought down to 2% SO2. So quite naturally what we do is basically we find out G dash, which is the solute free gas flow rate and which remains constant all through. We are going to use fresh water. So naturally, mole fraction of SO2 in my water that comes in is 0 and corresponding X0 is also 0. Now what we do is, we look at the equilibrium data which is available here. It's in mole fraction directly. Corresponding to this particular yn plus 1 is equal to 0.2, which is approximately somewhere in between these two. We find out that by interpolation the corresponding X value is this. Now this is the equilibrium concentration and mole fraction, and we in solute free basis we find this as simply Xn divided by 1 minus Xn. So that's how we get this value, which is the solute free basis. We write the overall mass balance equation in order to find out my L dash minimum. The change in concentration of L dash is basically from 0 to Xn star n, and in case of G dash it changes from Yn plus 1 to Y1, it falls in this direction. So based on this we find out that my L dash minimum is 236.35 with this unit. Obviously I have not repeated the unit here. What we consider now, we consider that my operating L is going to be 1.5 times the L dash minimum, and we get here simply 236.35 multiplied by 1.5 gives me 354.53. Now what we do again is basically we write the operating line equation here, and we know my range of interest in X will start from 0 and the maximum value can be Xn star. So what we do is if we take different values of X, it's possible for me to find out the other values of corresponding Y and plot the operating line on the X Y coordinate. We have done just that. Here what we have is the XY coordinate, here we have is the Y, and here we have the X. The equilibrium data is here. The corresponding to the L minimum, this is my starting point, which is the top of my absorber, and this is the bottom end, and we have noted that corresponding to Yn plus 1, what we have here is basically Xn star X, sorry, this actually is basically Xn star. So what we do here is we find out here in this particular case the operating line exactly the way I have said is drawn here. We make the first step by touching the equilibrium line, going up, coming to the horizontal again, touching it, going up, and these points correspond to the compositions x1 y1 and x2 y2, and this I keep on repeating. You will notice one thing. In this specific case, how many stages we have considered? We have considered 1, 2, 3 and 4. And in the fifth stage, if I go, the fifth stage gives me or allows me to have, instead of 0.2, possibly something around 0.26 inlet concentration. And instead, ideally, if it is possible for me to find out if I can really provide 4.1 stages, we will be too happy to do it. So basically what we find here, that we require 4.1 ideal stages here, or we can say that we require slightly more than 4. So this is the way you find out the number of ideal stages in this specific design problem. If you want, you can repeat the calculation yourself. Now comes the main problem, realizing the number of ideal stages in an absorber. We have found the ideal number of stages, but what we have to do now is, the trays won't be 100% efficient. So naturally, if you are going to provide a tray tower and I know its overall efficiency, number of actual trays is equal to number of ideal stages divided by this. Typically, if you are going to use sieve tray, possibly you will have a efficiency value of 0.35 to around 0.4. So quite naturally, if I am having 4.2 multiplied by, and I consider an efficiency of around 0.4, so you understand it will be around 10 trays actual. Now we talk about the other consideration, that is, it is not essential that you are going to use absorber where you are going to use trays. You are going to use a packed tower there. Let us see how you find it out. In that particular case, we know height equivalent to a theoretical plate, height equivalent to a theoretical plate, what does it mean? It means basically what exactly is the depth of packing required to provide one ideal stage of contact. We know 4.2 in this particular case has been the total number of ideal stages. So what we could say here in this particular case, my depth of packing should be 4.2 times HETP. Now remember, this already has the cushion of HETP because it's height of the real packing, the active packing length for the transfer. Now there is something here. Height equivalent to a theoretical plate is basically a theoretical, rather it's a practical estimate. Normally, tray vendors and other packing vendors will tell you be telling you how to estimate this HETP and what exactly is the correlation to be used. It is obvious that HETP has to be a function of the mass transfer coefficient, the packing size, the flow rates, and actually basically the mass transfer itself. Now we are still solving the same problem. Say what we have a reference here which gives us an idea that how to estimate a tower diameter in case of a packed bed. What we have here is d equals 4.5 into the velocity, rather the flow rate of the vapor in meter cube per second multiplied by a dimensionless factor. If I do this, in order to find out QV, we need to find out the condition at the top, at the bottom. It is obvious that at the bottom you have number of moles more in the vapor phase, but at the top usually your QV will be higher. So normally you will be evaluating the QV at the top and the bottom, and you will be taking the QV of the higher value. Now based on this, you will be finding out the diameter. You will also note one thing. Your QV is basically, in this specific case, what happens, the molecular weight initially is 28, it's very close to 29, and the molecular weight is close to 35, and as it goes up it's close to 29. So number of moles here will be slightly more, and that gives you normally a slightly higher QV. Now after you have estimated this, it's time for you to estimate the HETP. HETP is found from various correlations, but for vapor liquid contacting there is a simplified method which is published in 2000, and it goes like this. It involves the pressure of the column, it's for low pressure column, and ours is a low pressure column. P is the system pressure in millimeter mercury. Rho g and rho l are gas and liquid density in kg per meter cube. UGS is a superficial gas velocity in meter per second, and FV is UGS into square root of rho g. And in this expression what you find is, after all, if you evaluate your problem with these known conditions at the top and the bottom, you will find there are two differences in HETP, but the differences are not high. I have already calculated this using this particular data here, and we get a very small value of HETP, and this comes typically close to around 0.0 0.073 meters, say 0.1 meter, which makes it around 10 centimeters. You will notice one thing. It is a system in which you have a sufficient difference in the density. You also have a sufficiently low viscosity also. That means you are expected to have a good mass transfer coefficient, and based on that the generalized correlation gives us 10 centimeters of packing depth, and with around 4.2 stages it will be about 42 centimeters of depth. Roughly I will round it off to about 500 millimeters, or I will be using half meter of active packing depth. In fact, if you look at the value of the D itself, the value of the D itself is also not much. What you have is basically a much smaller value, and your D comes to approximately 17 centimeters. There is a thumb rule, in fact. Sometimes it is said that a HETP is close to the diameter value. Here we have a diameter of around 17 centimeters and we have a HETP estimate to be around 10 centimeters. We find that this particular thing is also fairly okay, and this thumb rule is also often used. I think with this I have given you a gross overview of the absorption in the 3 classes that we have concluded, and what I intend to do right now after this is we will think of real towers and the tower internals for mass transfer, and we are expecting to focus primarily on the vapor liquid contacting towers. To start with, we will definitely see what are the different tower types and how they are to be chosen. Thank you. Thank you all for today.